So let's start. Yes? Okay, so I have a long way to cover today, and it will be technical and maybe painful. So put the seatbelt on and let's go. Yes? Okay, so super quickly, this is where I finished the lecture yesterday. So we learn what is the chiral superfield, that it obeys this constraint. We define the covariant derivative properly so that the derivative of a superfield is still a superfield. We define this nice little trick with a y, so that then the nice thing was that y obeys this condition, right? So then I can immediately write this beautiful equation down. And then Taylor expand, you get this equation, yes? And we look, and what do we see? We see a complex scalar, we see a Weil spinor, and some other guy that is a complex scalar that we don't recognize, yes? And part of today, the beginning of today, will be to understand this table. So when we did massless representation theory, we learned that the n equal to 1 Wezumino multiplet has 2 degrees of freedom from a complex boson cell and 2 degrees of freedom from a Weil fermion on cell. And what we are discovering here is a way to go of cell. So this auxiliary field, because it's complex, is going to give us a way to balance the off-cell degrees of freedom of the Weil fermion. But this we will build up, and we will believe it more and more as we go. So the first thing I need to do in order for you to believe this statement is that I need to write down the supersymmetry transformation in components. Yes? So what we learned yesterday is that this is the superfield version. And now I take this equation as it is. Remember that Q is derivative with respect to theta plus something with a normal derivative, yes? So first I just project, so I set theta to 0 immediately, and I get this, the component now. I continue, I take one derivative with respect to theta, and again I set everything to 0. Not everything is the thetas. And I get this equation. If you don't immediately see this equation, open your notes in the page where I wrote Q explicitly, and you will immediately see it, basically. And then we have one more. So I take 2 derivatives, and then I send all the thetas to 0. And I get this. So this I am proving as I go. I'm not done proving. Now you can call it a stupid observation. This is on cell. We agree that this is correct. We agree that this is correct of cell. I know that there is somewhere lurking an F, and it's a complex field, so I put it, it looks like it's balancing, but as I go, and especially when I write down the Lagrangian, it will be clear that this is that. We have to do this and more that I will do all, yes? So let's actually really just do it. So if I want to kill this F from this auxiliary, because what I said yesterday I said that I want to find the superfield that can contain my Wezumino multiplet. So that's what I am trying to do now. And I found something that is very near and has these guys in it, yes? So now I am looking, what would happen to my counting if I set the auxiliary field, I don't call it auxiliary yet, this F guy to 0. If I set it to 0, okay, it will go away from here, but also the transformation should go to 0. If also delta F has to be 0. Yes, otherwise I'm doing bullshit. But if I do that to 0, what do I get here? This is the equation of motion of the Weyl spinor. So I go on cell. So this is very good. Yes, so my table seems consistent, at least from the point of view of this transformation. Is this clear to everyone? And to really finish the job, we will write down the Lagrangian, and we will do this basically immediately. So, what did we learn yesterday also? We learned that if I have the integral of any superfield, this is SUSY invariant, right? Okay, up to total derivative. So this is how you kill the total derivative, yes? This is what we did yesterday. Phi is a nice superfield. I want to put it here because I want to make a Lagrangian for phi. And let me, in fact, do the following. Let me put phi bar phi. Why this is good? First, it's supersymmetric. Second, it's real because it's phi phi bar, yes? Amazing. One more thing that now you will help me do. What is the mass dimension of this gadget? So let's do the mass dimension. In order to do this, let's look here. What is the mass dimension of phi? What is the mass dimension of psi? What is the mass dimension of theta? Amazing. Theta. What is the mass dimension of F? Thank you. What is the mass dimension of d theta? Sorry, plus. What is the mass dimension of this square? 1. Yes? So, what is the mass, and one last question. What is the mass dimension of the superfield? Yes, so 1. Fantastic. So, if I write this gadget, what is its mass dimension? 1 plus 1 is equal to 2 plus 1, 3, 4. Let's say the Lagrangian part, because the action is 0. Yes? So I wrote, just by doing stupid counting, something that is very good. This can actually really be a Lagrangian. Good? Are we happy? Okay, so now we will go to components to look really if this is nice. How do we do that? I will teach you also a nice, so this, today there will be a lot of tricks because you should be able to calculate in life and calculate fast and efficiently. So we will learn many, and here comes the first one. So I want to do this integral. Yes? And the first thing we learned is that we can exchange the thetas with derivatives, yes? I had this formula with 1 over 4 epsilon alpha beta de alpha de vita, yeah? So this I can exchange, and okay, you should also always think that there is a dx all over, so that whatever is the total derivative dies, yes? So this, I want to exchange it with a d squared. Yes, that's what I want to do. So now let's make a little observation. Phi bar, phi is chiral, phi bar, anti-chiral, amazing. So if I hit it with D, I get 0. So I can cross, and I can write this. Okay, let me drop this so that I don't have to repeat it all the time, but I will drop total derivatives, yes? You will forgive me. Yes, so I have this. And now I have this. and there is a little bit of this quarter thingy. Yes? Is it clear? So now I take my beautiful equation here, and I copy-paste what survives after I took two derivatives, which is basically sitting on the second line, up to and this guy, this beautiful guy also. So this is, this goes away. This I don't copy because I didn't do anything to it yet. There is an I. Okay, I am trying very hard to not copy wrong things, but you have to check me, yes? So that's what we have. Yes? So now I need to do still this. So when I multiply phi bar with whatever sits here, the only things that will survive life are the ones with two thetas. Everyone else will die. But this is very easy. So with this, phi bar, f bar. Yes? With this, what should I do? I need one more theta. Yes? Yes. Yes? Yeah, I forgot a psi. Thank you. That's pretty crucial. Otherwise, there will be no fermion there. Yes, thank you. That's amazing. So this baby has one theta, and when I bar this, one more will come from here. Yes? Oh, so this also is looking very good. Yes, this is what I get. And what about here? It has already two. So I will get the first baby here. Yes? Yes? So, but this looks amazing. This looks like a very proper kinetic term for a Lagrangian, yes? So the crazy counting that we did there actually bear fruit, and it gave us something really nice. So if you want to get kinetic terms for a chiral superfield, this is what you do, phi bar, yes? Now a second comment. What is this guy? You have seen this. So this is a kinetic term. It's a baby that has dimension 2, and its kinetic term doesn't have derivatives. You've seen this when you did solid-state physics and you learned the Hubbard-Stratonovich trick, right? It's an auxiliary field that you can integrate out. If I would integrate out at this stage, it would be just 0 and it will be gone. When I will write interaction, it will be a little bit more, but still it's just that. Is everyone okay with that? So this really now deserves to call the auxiliary field. And is really just there to balance the degrees of freedom. Yes, I do equations of motion and I kill it. And I go to the first line. Let's make some more comments. So, comment number 1, at this stage, and I will almost not write anything, whatever we did, we can add another index, an index I to phi, and we can just repeat everything with indices everywhere. Nothing will go wrong. I just do it on the top. So let's say we have many phi's with I goes from 1 to n. No problem. I, blah, blah, blah. And basically here is important that you write it. Yes. And here is the Lagrangian of many of these guys. No problem. Yes? Second little thingy. What happens? I actually do this. So I imagine that inside my superspace integral, I put a more crazy function. What happens? Well, some things in life you have to be careful about. First of all, let's formally write this. I formally write as a power series. At this stage, I am completely random. I don't know anything. It's some formal power series. But this guy is supposed to be a Lagrangian, yes? So first of all, if I do this, it should better be real. Otherwise, it's not a good Lagrangian, yes? So for this to be real, I need that Cn, m star is equal to that. Otherwise, problem. What else? So we know how to get normal kinetic terms. Clearly, if I have crazy stuff going on, I will get higher derivatives, things will break loose. But this is fine. Like when we do effective field theories, we do something crazy in the UV, we give a VEV, we let it flow, we go to the IR, we get effective field theories. The only thing that we know very well will happen is that these coefficients, they are going to have mass dimension, yes? So that in total, the gadget looks like a Lagrangian with 4, mass dimension 4. And so lambda is the scale of the CFT, of the EFT. Yes? No problem. What else can I say about this? Let's try to not delete this for now. And maybe also this, not delete for now. So, yes, please.
The composition of the function k in that way is generic. There is an example. I lost the part in which you.
I'm like, what if I do this?
Okay.
I'm crazy. I want to try this.
Yes, but
Yes, why not?
Kind of a power series.
This is just a super crazy formal thing. It's just a formal expansion so that I can actually say something. And I see that I can say these two things. Formal. Okay, this is one thing. Now another little thing. What if all of these are like note this, note that? I add to my Lagrangian here phi plus phi bar. Now linear. What if I add this? What happens? First of all, phi plus phi bar is very nice, real. It could be a good Lagrangian, right? But let's look. We did the calculation basically there. We just have one less phi. What is it that we get on the right-hand side? If this baby was not here, and I have to do this integral, I kill it, and only this guy will give something. What is this? This is a total derivative. Yes? Let's do another what if. What if I start with my crazy guy, formal, and I add to it so now lambda is a holomorphic function, and I start now with this holomorphic, and then it will go amazing, but this is the first time. Which means d lambda d phi bar is equal to 0. Yes? No phi bar in it. Yes? What happens if I do this? It's the same. This is all total derivatives. And to see this like really with your eyes, you can just kill this with your hand and put this many times. There is nothing you can do, only total derivatives. Yes? So this is serious. And in fact, you can say that this is the symmetry of the theory. So k going to k plus lambda bar is the symmetry of the theory. And this is basically what, when we learn complex geometry, these are Kähler transformations. So these are called and because of this k function, we call it the Kähler potential. Yes? Are we good? Okay, if we are good, we continue. And now, okay, beautiful, we made kinetic terms. Let's do a little bit more advanced something, yes? I want to make interactions, and interactions that are not maybe, non-renormalizable. Let's try to find a way to make renormalizable interactions. Yes, let's try. Let's make first a little comment. So what did we do? We said of any superfield, this is supersymmetry invariant, right? But what can I do is that I can steal this baby, I did it before when I did my calculation, and write it as covariant derivatives. I dropped the factor because I don't care about it right now. Squared. This is like this now. But what is this guy? If I act with a further d bar on it, I will get 0 because 3 of the same spinors, 0. Yes? So this is a general superfield. But now this is a chiral superfield. Three derivatives, they give 0. Yes? So what did we learn? If this is supersymmetric, this is supersymmetric because they are equal. So what we just learned is that if I integrate only half of the superspace, but I am integrating a function, something, any superfield that is chiral, this is also supersymmetric. So this D, now I'm using the notation I want. And this alternatively, you can say that W is holomorphic, like what I said there. It doesn't have phi bars in it. Yes? So if W is holomorphic and only it has phi's in it, it's chiral. And if I integrate it over half of the superspace, this is supersymmetric. Maybe I write here. Yes. Is this nice? Clear? So if this is clear, this is amazing, because I will use this to make supersymmetric interactions that are not non-renormalizable. I should say that W is called superpotential. That's just a name. So let's do this. And because I need it to be real, I always need to add the Hermitian conjugate, yes? So the Hermitian conjugate is d theta bar, W bar of phi bar, yes? So this is going to be my guy. And let's just make an immediate example. I already said that Wes and Zumino are the heroes of these. Okay, they didn't write superspace when they started, but I will write for you now in superspace the Wes-Zumino model. Here it is. Nice and simple and beautiful. Let's do counting, because we can count now. What is the mass dimension of phi? If G is massless, what is the mass dimension of this term? Yes. Now, if this is a mass, what is the mass dimension of this term? Okay, so this amazing superpotential that we wrote now has mass dimension 3. And it needs to be integrated over this. What's the mass dimension of the theta squared? So we made a very nice Lagrangian that is marginal, right? Yes? So this is the most normal thing to write in this life, yes? I mean, okay, this is marginal, this is clearly relevant, but anyway, it's clear what I'm saying. Yes? Are we happy with this? So if we are happy with this, we will also go to components to see how it looks for the real physics we know in the normal fields. Let's do this. Okay, I will keep this for a little bit more so that you can immediately go to components without thinking too hard. Show components. And there is no trick now because it's so easy. So I want this Lagrangian. I could do it for this, but I will just do it for the general one, yes? Just to be done once and for all. Okay, so I have to do 2 theta integrals, and this is a function of phi, and I look up. Yes? So what can happen that is not 0? Let's say, for example, like for a little second, for example, if I had something like this, one of the things that I would kill is the theta theta in the auxiliary field. So there will most definitely be a term that will, okay, have an annoying minus. It will have an F. And then it will look like this. By the way, let's go a tiny little bit slow. When I write this, what do I mean? I mean, take your W, that is a function of the superfields, take the derivative, and then set whatever thetas are there to 0. And that is just a little annoying notation. Yes? Is this clear? So I will definitely have such a term. We all agree? What else can happen in this life? For example, there is a term with a psi there, and it has a beautiful theta with it. So if inside here there were two psi, for example, like here, I would already have psi squared that after the integral is what I get. So what is this? First of all, there will be always a half because I don't know to which I act with the derivative first, so I always get a 2. And then I will have my 2 psi's, properly contracted as always. Yes? Is this very clear? Yes. This guy. Look at this term. Or this. Honestly, it doesn't matter. In order to get something with 2 thetas, look upstairs. There is the theta psi guy, right? So if I multiply 2 of them, phi capitals, I will have theta psi. So I will be remaining here with a mass, or here with a g phi, theta psi phi. And the 2 takes into account that we don't know where we act with the derivative because they are identical. And basically that's it, because there is everything else has other structure of derivatives, so in the end it will just give 0. So the answer is this, plus the conjugate. That's how I make interactions. And if I translate this for this baby, I will have a term that is f m phi, and I will have another term which is psi phi, which is a Yukawa type of term. Yes? Amazing. So this is what it is. First of all, the total Lagrangian, I need to add the kinetic plus this interaction that we just made. And as I will say, this is an off cell. Why is this? Because it has this auxiliary field F. And now I want to integrate it out. Yes, to show you what happens when you don't have it. So how do we do this? There are 2 ways to do it. Either you consider the path integral that has an f bar plus linear terms in f, and you do your beautiful quadratic integral you all know how to do, Gaussian type, you complete the square and you do it. Or more easily and stupidly, you just do equations of motions for f and f bar. So for f, because this multiplies, there is f bar and this multiplies this, I'm gonna get the complex conjugate of that. Is this clear to everyone? And once I have it, I go and I plug it back in. And I get the on-cell Lagrangian, which is the kinetic, okay, that I don't repeat because I'm bored. And then absolute value squared This is a 2. It looks more like a worm, but okay, this is what it is. Yes? So now, what is this little guy here? This guy only has scalars in it, so it deserves to be called a scalar potential. And it also, you can say that it came out of F bar being integrated out. So this is how we get a potential in supersymmetric theories. And by the way, look at it, how nice. It's the square. So this is always positive. If you plot for a supersymmetric theory the potential, it can do whatever crazy thing it wants, but it always has to be above 0. Yes? You can go below only if you do something and break supersymmetry. As long as you keep supersymmetry, this is how it can look. Yes? And maybe one last comment. This, what is this? This is some type of scalar multiplying psi psi. This is some type of Yukawa terms. So that's what we have. And if you want to make your life very simple, you look here, for example, right? What is this? This is G phi psi psi. Really Yukawa, the one you know and love. What about this? This gives a mass term for the two fermions, M psi psi. What about the potential if I had this baby? Phi to the fourth, G phi to the fourth. Yes? What about this? M squared phi squared, the mass term for the scalars. Yes? Is this clear? Okay, if we want to do this slowly, we can do it for the Q&A. So I think I am more or less good with these guys. I will say one more thing, which I said already before. So before, what did I say? For every phi, you can have many of them. Who cares? How you can have phi I of them. So what do? You go and you put i's everywhere. And you get the Lagrangian of some type of sigma model. And also, as we said before, when I said these comments that there are these non-renormalizable things, you can go as crazy as you want. So you can make the most general Lagrangian with phi i's. Yes? And what is that? That's full superspace integral, crazy function of however you like it with the constraints that we said for the reality, yes? Plus any holomorphic function of these babies, plus its Hermitian conjugate. This is the most general n equal to 1 Lagrangian with only chiral superfields. And there is one tiny little comment, and I'm done with this. When we derive the kinetic terms, here you can have as many phi's as you want. Think of this formal expansion if you want. So when you derive the kinetic terms, you will get a term that can be a function of these phi bars. Should be consistent with my own notation. It can look like this. Yes? This is totally allowed. And this is what people call the metric of the sigma model. Yes? But, so maybe I write this. But one thing, we learned that there are these scalar transformations. Yes? And by the way, this metric, how did I obtain it? By taking two derivatives with respect to this. So, it's like this. And here we explicitly see also in a different way why the scalar transformations are a symmetry of the theory. Because from here they cancel. And this maybe you have studied if you did complex geometry. So this is the scalar, the metric of a scalar manifold. Yes. Nothing. A scalar manifold is just complex manifold with the condition that the metric is obtained by this. And clearly by the stupid equation, it has the symmetry that if you add holomorphic shifts, nothing happens to life. That's it, nothing else. And this manifold is a manifold that has coordinates. It has the phi's and the phi bars. And in string theory, this comes from the Calabi-Yau. But who cares, right? Now we are doing supersymmetry. Yes? Are we happy? If we are happy, we will take the next step, which is gauge fields. Yes, it's time for gauge fields. Enough with the stupid scalars. Let's do something more interesting. So I want to have n equal to 1 vector. I want a Lagrangian for that. We learned the massless multiplet. We want to put it in a superfield and then make Lagrangian for it. Yes, this is the schedule. Is everyone ready for this? Okay, let me start by making a table because this is what is good to do in this life. So what is the field content of the n equal to 1 massless vector multiplet? It had a nice little spinor guy, and it had a gauge field, yes? And on cell, when we did it, we said that this is a Weil guy on cell, so it has 2. And the gauge field on cell has also 2, because we have said -2 for the gauge fixing, -2 equation of motion. What happens if I go off cell? This becomes 4. There is no equation of motion anymore. And what happens here? The gauge I always need to subtract. So this is always 3. So they don't match. So, you know, if you take inspiration from when we did the other table before, what you really need to add is an auxiliary field, let's call it D, that, of course, when it's gone, it has nothing. But when it's there, it makes the degrees of freedom match. So only 1 degree of freedom. So we need a real yes? Hey, if you need a real, I will make you a real. It is very simple. When I wrote the most crazy superfield, in the end I had a term with theta, theta, theta bar with some random d. I will make this real. So how I will do it? I will impose the reality condition on the superfield itself. I mean, okay, I also know the answer. I admit this. But I will do it and you will see it coming out. Yes, I admit that I also know the answer. I would not be so fast if it was the first time I was discovering everything. Okay, so now for like a minute or two, I have to write this crazy condition, what it does to the total guy. And you will have to be patient with me, and I will write everything out as nicely as I can, and you will find my typos, yes? So what I will do is that I will take the general superfield that we had before, and I will make sure that it's real. Yes, that's my task. So let's do it. So, okay, first of all, the first thing, it just has to be real. So C is real, I just say that. But now more non-trivial things happen. I put an I there, this is just annoying notation. So if this is my first spinor, this is what I need to do at this level in order to make this thing real. Yes, real up to now. I continue. Okay, there are some factors sprinkled, but it's, here I don't want to have this first. I go here. So this, I had this term, as long as A is real, which is going to become my gauge field, so I want it to be real, I am very good. So real up to here, yes? So now, I want my theta theta, and then the theta bar theta bar. And I will just write it out very explicitly. So this is some baby. And as long as I add its complex conjugate, so now n and m are real functions. Yes, I'm writing everything explicitly. Up to here, I am very real. I am adding something to what I was writing before, which maybe you can even skip paying attention. It's just to make some things nice. But I have to, so this is the full glory. You can ignore it for now. It's very hard to understand just by looking why this crazy person is doing this. Sigma mu. Yes? And last but not least, theta theta, theta bar, as I promised, d of x. I already used my notation, so that this is this baby, real. Okay, and there is a little bit more that you shouldn't know why I am doing it, but as long as it's real, I can do it, so it's okay. Yes? Is it real? Yes. How many degrees of freedom is in this beast? So all of these are real? Yes? So we have 8 bosons, 4 scalar, 4 real scalar, and another 4 without imposing anything yet by A mu. And 2 Weil fermions are in here, this chi and this lambda. So another, yes, this is my degrees of freedom in this gadget. This is not so good. This is very far. Yes? I need to find a way to half it. Yes? But okay, actually, it's very clear how I will do that. I still didn't do the most important thing. I want to have a gauge field. So I need to gauge fix. Yes? And I will do this in a supersymmetric way because we are in super space. So I have to add something to the game. a superfield that takes into account the gauge fixing that will basically precisely kill what I need. What is the degrees of freedom of a chiral superfield? Of cell. What we just did. It had a phi, an f, and an off-cell vial. 4 plus 4. Okay, so what happens if I say V goes to V plus, okay, I will call it Xi. It's ugly, but that's what I am doing. First of all, is this real? Yes. So I didn't spoil my constraint. Yes? So this is going to be my gauge transformation now. And my gauge transformation is I will now write it. I want to make it a chiral superfield so that it precisely takes out the degrees of freedom that I don't want to have. Is it clear what I'm doing to everyone? It will become clear also when I go to components, and it will become amazing clear. But at this level, I'm just counting degrees of freedom. And we need to go to components to see that this is really what we really need to do. So let's just go. So Xi is a chiral superfield. So I will use again my trick to write it out. There is this annoying square root of 2, unfortunately. Okay, I am calling it Xi because I don't know what to call it. Forgive me, I don't know. It's a fermion that belongs to Xi. Yes? And I'm calling this F Xi. And now I will take this equation, so this gauge transformation that I wrote there, you can call it my conjecture, and I will hit it, I will go to components. First, just go to components by setting the thetas to 0, then take one derivative, set everything to 0, two derivatives, everything to 0, bam, 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 like this, yes? So I write it. So C, which is the first baby, will go to C, but it will get corrected by the real part, because it's Xi plus Xi bar. Yes? Continue. Chi will get corrected by minus this guy. Okay, I don't write chi bar because we will all lose our patience. M goes to M minus 2, the imaginary part of this F auxiliary field of Xi. Okay, there is the same for N. I don't write because I don't have patience. D goes to D with no further shift. And most importantly of all, A mu goes to A mu minus 2. 2 is a factor, is nonsense. I will just maybe write the derivative first. This is what you get when you go to components. Look at it nicely. Look at this. Do you recognize something in this equation? This is what we learn when we learn ENM. The imaginary psi with this annoying factor of 2 is precisely the gauge parameter. I'm doing a billion now. First baby steps. Yes? And also, super nicely, this D, the auxiliary field, doesn't transform, which is a nice... Oh, there is another thing that was important that I should have written. Lambda also doesn't transform. This is also very important. So these are important. Yes? So now everything looks very nice. We have a gauge transformation. And now the name of the game is we want to get rid of all of this annoying junk. Yes, because we don't want them. We only want a lambda, an A, and a D. Yes? According to my beautiful table up there. And how do we do it? We gauge fix. Yes? We will do a supersymmetric gauge fixing. It's called Uesumino gauge, because we said that these guys are the heroes of these lectures, so they did more or less everything that is important that you need to know up to tomorrow, because tomorrow there will be another hero. Yes? So what is the Uesumino gauge fixing? Get rid of this. How? Choose psi such that the real part of it cancels C. Choose this such that it cancels this. And in this way, you can get rid of all this junk and be left with what we want. Yes? I just write. Choose C. Or actually, what you choose is the gauge field, not the C. So you choose this. You choose that this guy is equal to C. You choose that this annoying thing is equal to psi, and so on. Yes? And what you are left with in the Uesumino gauge, V becomes very, very simple. It starts with this term, because all the previous junk is gone. It has the gaugino. And the auxiliary field. And nothing else. And it's nice. Sorry?
The other terms are gone and if applied, they will
So right now, the gauge fixing that I did fixes all this other junk, but in fact, psi is a complex field, so it has a real part and an imaginary part. If you keep the imaginary part of it free, you keep the gauge, so you haven't fixed the gauge, but you got rid of all this other junk. So there is one parameter there that you can still keep and play with. One very important thing, if you keep this guy free, You are breaking supersymmetry. Yes, the way zoom in, I will write this because this is actually very important and people don't know it and make mistakes, and this is how you can destroy papers that are submitted and not accept them. The way zoom in gauge breaks supersymmetry. So you really need to be careful. Yes? You either fix all the way, the way Zoomino gauge, everything came into this Xi, which is, I don't know where it is now, it's gone. Yes? So you keep supersymmetry only when you have the whole Xi. Yes? If you start fixing things, you break supersymmetry. So when you calculate in the way Zoomino gauge, in the end of your calculation, first of all, you need to know what you are doing. You need to know that at this stage of the calculation, it's allowed to fix. And also, in the end, you need to check that what you did makes sense and it's not completely crazy. Yes? Don't just calculate. Yes? Yeah, you have to be very careful. You have to be very careful with this. You're extremely careful. You have to always check. You have to always check. Yes.
And if we also fix the imaginary part of psi,
Yes. So when you fix the imaginary part of Xi, you have to be very careful when you check your supersymmetry, what comes on the right-hand side. You may get gauge artifacts. You always have to check. So this is serious. Yes. But nonetheless, because if I wanted to do now the most general thing, I would have to kill myself and you. I will now gauge fix. I will be careful, I promise. And I will do all of my calculations from now on in the Wezumino gauge. Yes, but I told you the warning. So, first of all, it's nice because of this, but there is further niceness in this life. And this we definitely need. In the Wezumino gauge, the square of V, all of these guys cancel, and that's the only thing that remains. And by the way, this was the question yesterday. When you square this, you use this identity with a sigma sigma, and you get so theta squared is just this. And then if you compute higher terms, they are simply 0 as long as n is bigger than 2. Yes? So this is going to make life pretty nice. It's pretty handy to calculate like this. Are there any questions? Yes, please. Yeah, I can delete it. You can say that it's by definition. By the way, there is a bar missing also. You can say that it's by definition just because things look nicer. I define D like that. Yeah. Is it okay? Whenever you have something real, it's very important. For example, when you write a kinetic term for a real field, you write 1/2 d phi, right? If it was complex, you would write d phi bar. So it's nice to have these twos. But no physics. Yeah, here I should have put a half. This is what you're saying. Yes, this is true. Put it, and I will delete now the blackboard. Because I need to write something else. Yes? So this is here. Yes? I forgot. Okay, I delete. I start from the top so that you have time to put the two. So, what happened is that we have now the super version of the gauge field. What about the field strength? Let's first make the equivalent of the abelian field strength. I will write super. Yes? So I want to make the equivalent of F mu nu, which for abelian, for Maxwell, is invariant under gauge. Yes? Okay, I will just, so we are doing this. And I want to guess an object that if I do this, it will stay the same. And it's pretty easy to guess this object. Okay, up to, of course, annoying factors that mean nothing, but they are put there. So this object, I claim that this object is invariant. Let's do this. Let's prove it. Recall that psi is a chiral superfield, so psi bar is an antichiral. Yes? So when I act on this baby with my derivative, it's gone. Yes? Here. So I will write delta alpha. So I don't repeat rewriting. Yes? So this is the only thing I need to check. So I only need to check that, okay, there is this annoying. So that's the only thing I need to check because this is gone. Yes? Now I am doing this calculation not because I want to do all the calculations and I want to be annoying, because I want to teach you another trick. Psi is chiral, right? So d bar on psi is equal to 0. Yes? When we have such things, what do? This is standard trick that you will use in your life. We look here. This d, if it would pass this guy and act on psi, it gives a 0. So what I can do is that I can replace this by the anti-commutator for free. Yes? True? Everyone agrees? But what is the anti-commutator of 2d's? It's a derivative. So what I am having now, sorry, now I am dropping all the factors. I'm a horrible human being, but who cares, all the indices. But so I am having this d that went down. This anti-commutator is a derivative, and psi. What about commuting d bar with psi? They commute. So what happened here? Okay, forget about the stupid factors. Derivative d bar on psi, this is 0. 2d. Yes? And this is an important trick to learn in this life. Yes, and this is a two-liner, but maybe when there will be more lines in this life, this will save your life. So, W is invariant. What else is W? Look. Can someone tell me a property of W that can see just by looking at this blackboard? Thank you, this is amazing. And because it's chiral, I will write it now with my y so that it looks beautiful in components. Yes? This is a tiny little bit of a calculation, but I will trust that you can all do it. So I will just write down the answer. Okay, let me check that I didn't write something crazy. Yes, it looks quite perfect until you find a mistake, but yes. Yes? So this is something super easy to check that it's true. Now, this is why I wrote it, not because I am crazy, because I want to make my life from now on as easy as possible. And what do I want to do? I have my superfield and I'm happy. I want to write now a Lagrangian. Yes? And you told me that W is chiral. Yes, you told me, I didn't say anything. So W is chiral and gauge invariant. So I want to make a beautiful Lagrangian with it. And let me ask you also one other question. What is the mass dimension of W? 3/2. So if I have two W's, which is also important if I want to contract the index, how much is W squared? 3. What was the mass dimension of the superpotential if I wanted to get a Lagrangian? Yes. So this is what I need to do. I need to write down yes? So with all these nice things that we are learning, this is a scalar. It's chiral, so half superspace is enough. Its mass dimension is 4. And okay, I will do this in a second, but if I add Hermitian conjugate, it becomes real and it looks like a very good idea for a Lagrangian, yes? But let me first write this out. And how do I write this? I take this and I plug in, and I just keep only the guys with 2 thetas. Yes? So, trivially, I get from here together with here, 2 thetas. Oh, this looks like a nice kinetic term for a fermion. Yes? Don't worry about the overall factors now. Now the overall factors will look slightly ugly, but in the end they will become nice. We have the d baby, 2 d's will integrate 2 thetas, d squared. Now, here, what would we say about f mu nu? F mu nu is antisymmetric matrix, 6 degrees of freedom. I split it into 3 plus 3, self-dual, anti-self-dual. What did I explain with this sigma mu nu? It has this beautiful self-duality property. So let's use it. Let's replace this sigma mu nu by a half, and then half of it plus that. Yes, just because I want. What do I get if I do this? I will get like that. Minus a half. There is one of them, one more if I have another time. 1/2 f mu nu, f mu nu from the first part of the identity, plus I, because the I wanted to go up and it came from the other side, divided by 2, epsilon mu nu rho sigma, mu nu f rho sigma. That's what I get if I do the 2 theta integrals. Yes? I mean, you can spend a little bit of time checking my factors, but I mean, it should be pretty obvious that this is what we get. So as I said, I will add the Hermitian conjugates, and I will get the Lagrangian for Maxwell. Electromagnetism, it's n equal to 1 version. So what happens if I do this summation? And now there is an overall, but I ignore the overall by now, yes? There might be 1 over 2 e squared, like, forget for now. So up to factors. What is this? Because I added two of them. There will be this annoying 4 that I will take care of later. And our beautiful friend, the auxiliary field. And this bad guy cancelled. Yes, because I plus dagger is minus 0. Yes? And this is good. This is the Lagrangian of electromagnetism, together with a kinetic term for the gaugino, together with its auxiliary field. Also, the auxiliary field is something that is squared. It is a proper auxiliary field. It's just real in this case, but it's all very, very good. Is everyone very happy? Is there any complaints? Yes. So this is, yes, this is the table. Yes. Yes, that, like everything I did it so that I can arrive at this. What is the other side? Before gauge fixing is what I said. It's 8 plus 8, and you have to suffer. By the way, there is a very beautiful paper and the PhD thesis of Stefano Kovacs, more than 10 years ago, maybe more than 15 years ago, who keeps all these auxiliary fields and writes everything out. And it is an instructive thing to look at. Maybe don't do it by yourself because you have to write a lot, but at least look. So look at the PhD thesis of Stefano Kovacs, or he has this paper called whatever, n equal to 4 super young males, something, not recalculating, but something like this. Reanalyzing, something like this. And he keeps everything, and you see how they are auxiliary. He computes Feynman diagrams with that. He shows that if you don't take into account the gauge properly, you will get wrong things. It's very nice. Are we happy with this? So if you are happy, you know how to do electromagnetism, supersymmetric electromagnetism. And now there is one thing left in this life. We need to go non-abelian. Yes? Let's go non-abelian. There will be a little bit more pain now, but it's okay. Yes? And yeah, let's just do it. So clearly what I need to take care and to improve upon is, first of all, what I call V. What is this V and how it transforms? Because clearly non-abelian transformations are more intricate. And then what is the non-abelian version of F mu nu, the field strength? That also I need to improve upon. Yes? So let's just do it. So first of all, again, the abelian guy is V. I will do a slight change of notation now in order to match Bertolini so that, basically I can check my answers and I have no wrong factors. So I will write it like him. So this is like this. So psi went to I lambda, yes? But they are still holomorphic, yes, as they should. It's just this annoying I. Now, the non-abelian version of this, I postulate. It doesn't make sense to try to convince you that this should be like this. I will just construct something that makes sense. So I say that it's this. And just to make a first order completely stupid check, let's use our, how is it called, this identity that we used yesterday to put things down. So I expand and I get that V. goes to V minus I So look at this. So this is the abelian if you expand. And already the next term is a commutator, which is 0 if the guys are abelian. So it makes sense. And if you continue expanding, you will get more commutators. Everything goes to 0. So this is not insane. That's the first order. This is the abelian part. Now I also need to postulate something for the field strength, the non-abelian field strength. And then I will convince you that this was not a crazy idea by checking how it transformed under other gauge transformations. So this is postulate. Okay, again, annoying factors. This part is as before. Here is a little bit of a new thing. By the way, the part of going from abelian to non-abelian, it took people some years. So in the whatever 70s, when the super space people were inventing super space, there was a gap. It was very hard for them. So that's why it looks so ugly. It is what it is. So let's now transform. Let's do our gauge transformation. Yes? So W alpha is going to go to, okay, first of all, I just copy the factors. As long as there is patience, I will just be nice and copying the factors. In 1 second, I will write what goes here. Here, I just copy from here. Yes? So first there is plus I lambda bar e to the v e to the minus I lambda. Yes? And here, I need to write its inverse. Oh, this is very easy. If you start backwards, you can write the inverse super easily. Yes? So this is the inverse of this. Yes? Happy? Okay, now let's do it. Now we play our tricks again. First trick. D alpha, it can act here, yes? What is lambda? Antichiral superfield. Yes? Yes? So, look at me. I can kill it. D passes it, and then this cancels with this. Is this clear to everyone? Is there anyone that wants to complain?
I can pass the alpha directly on
Here I pass because of this identity.
0 and then
Yes. So this was my first step. Second step, D now can act only on here and on here. And because there are two things, I will write it out as a sum of two things where it acts on these two things independently. Yes, let's just write it. The rest I copy. And okay, very explicitly. So here I act only on this, and this little guy, and I will make a big parenthesis here. Yes, plus e to the I lambda. And when I skip this and I act on here, this baby will cancel with this baby. Whoop. Yes. Is this clear? But now look. Okay, maybe I write one more step. These guys, they are D bars, lambda is chiral, couldn't care less. Okay, maybe I will, how do I do it fast? Sometimes you shouldn't try to be too fast. This is the first term. Oh! Yes? Plus, I will say plus. Do you recognize this baby in the parentheses? This is the definition of W alpha. So what I derived here, the first term, is actually precisely a covariant gauge transformation for W alpha. So the rest better be zero, eh? Let's prove it. The rest better be zero. How do we do it? We bring our friends these inside. Yes? First of all, this is chiral. So these guys don't act on it or give zero, so they cross. And what happens here? We have the same trick as I did before. D bar, D bar, D, E to the... What is the trick that I did before? If I would cross this, I would get zero. So I replace this by the anticommutator. The anticommutator is a derivative. This extra D will cross the derivative. It will hit lambda and it will give zero. Is it very clear or I did it too fast? Make me do it again if you want me to do it again. I will do it. Or slower. Is it okay?
Just the meaning of the first term.
Yes, so I will write now. We will talk. Yeah. Now we talk physics. But first I wanted to make sure that the calculation is clear. So what we just proved is that W alpha under our supersymmetric gauge transformations yes, and okay, I didn't write this. I will write it so that I am very nice. But it's the same thing for lambda bar, so for W bar. Yes? And note that the one from the other, this is not the same as this. They are independent. So W and W alpha independently transform, the one with a chiral gauge field and the other one with an antichiral. Yes? I will write super quickly because I skipped, but this is not a good behavior. I didn't give you the definition of W bar. I mean, you should be able to get it just by acting with a dagger. But okay, I also just write it. And if you want to practice your D skills, you can also derive this equation from this, yes? It's the same. Yes? Amazing. Okay, now let's recall very quickly when we have a non-abelian f mu nu, how does it transform? It transforms with a u from the one side and a u minus 1 from the other side, right? Here, I go here. Basically, what I'm trying to say, and I will say it nicely and slowly, is that for the same reason, W alpha is also gauge invariant. But let's do it. So normal quantum field theory. Yes, how does this transforms under gauge? There is a u, f, u minus 1 from this first guy. Yes? This cancels with this, and this cancels with this after you use the trace. Yes? Nice. W alpha is the same. Yes? Cancel, 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 cancel. So W alpha is the way to go in life with a beautiful trace in the front, as it should, of course, because now it's a non-abelian beast. Yes? It's the same. Are we happy? So this trivially plus its Hermitian conjugate will give the Lagrangian we know and love. You just need to remember to put trace everywhere. So, no, it's all gone. You take the Lagrangian from before, you put trace everywhere, and you are very happy. There is one more thing that I will do now slowly, but that's it. Yes? Good. The Lagrangian that I did before, and that's why it's not complete, it was for the abelian part. So now I want to keep track of the non-abelian part. And this way I will write down for you the n equal to 1 super Young-Mills Lagrangian. So what is this? So first of all, we go to the Wezumino gauge so that we don't suffer too much. And in the Wezumino gauge, we take the e to the v, this annoying guy, and we expand it. I write here 0 because we are in the Wezumino gauge, yes? Okay, let's calculate. What is this W alpha now here? So I take and I expand. I skip one step because you are amazing and you can do high school algebra. Yes? Yes? Is it almost obvious? I mean, you can do it in your head, I guess. And what is this? So this is the abelian part. And this is the non-abelian part, which actually I can also write it in a nicer way as a commutator, which is very nice. So this I can write like this. This is a little bit nicer. Yes? Plus stuff that is 0 in the Wezumino gauge. Amazing. So I only need to understand what this junk is doing, and I am done. I will go to components. Yes? Let's go to components. In the Wezumino gauge. Okay, I just write the answer because I have deleted everything from the blackboard. This is actually super unfortunate. But this is, okay, this is, such is life. So that's what this is. Yeah, it's very stupid that I deleted everything from before. Yeah, it's okay. So these are the terms that I didn't calculate before. Everything else is the abelian part that I calculated. So let me remind you what was this. This was minus I lambda plus theta alpha d. Nothing is going to happen to these babies. But there was then I sigma mu nu theta alpha f mu nu. So before, this was the abelian part. Just dA mu nu minus d nu a mu. But now this is a non-abelian, so it needs this in it. And look at it, it came precisely with the factors that we need in order to go and become friends. Yes? So this is now the non-abelian. Sorry, I put factors. Ooh, there is a factor. I will fix this so that it looks like more normal quantum field theory. And there was one more term before. Theta theta, sigma mu, alpha beta dot. Before it was like this. D mu, lambda bar beta dot. Yes, look at your notes. What is this term? It will make the derivative covariant derivative, yes? Nice. So that's how we go fully. That's how life goes. Yes? So this is almost perfect and done. There is one thing that doesn't look good. And this thing that doesn't look good, because I just did randomly my calculations and I was not very careful, and I told you that I'm not careful, were the factors here. What is this junk? What is this? Is really not nice. When we learn quantum field theory, there is G. Young-Mills there, right? So in order to get G. Young-Mills, I will rescale all of my fields by a factor of 2, first of all, which is really annoying. And I will multiply also with the G. Young-Mills. Yes? I will write here. So I will send all of my fields to 2 G. Young-Mills, the fields. And maybe I don't need to say this in detail, all of them. The same for lambda, and the same for D. Yes, I have to do that. And now I am done. I am very, very, very ready to completely identify the n equal to 1 super Young-Mills Lagrangian in full glory. Yes? And we can do this definitely in 10 minutes. I just need to define one thing for you, which is an amazing thing in this life. And this is the so-called holomorphic coupling. Okay, here, because theta is the same as the superspace theta, we write Young. You can also write Young-Mills here if you want. So I define this because I like it and because it will make everything beautiful. And now I can write everything. First in superspace, and then in components. And in components, I don't have to do a new calculation. If I could copy paste with like my iPad, it would be just make the covariant derivatives. So here is it, full glory. Super young meals, n equal to 1, equals. Okay, because there are pi's there needs to be pi's here in the front. I'm sorry. And instead of writing W alpha plus Hermitian conjugate, I will write the imaginary part of tau, my coupling. Yes, so you already see that there will be 1 over G Young-Mills squared, as it should in this life. Yes, and then we will have half superspace integral, trace, never forget, now it's non-abelian of this. I can make this a square bracket. That's it. That's my baby. And I go to components now trivially. Trace. By the way, I always forget the trace. So I'm very proud of myself that now I wrote it. Covariant derivative, yes. Here is the beautiful one, half as it should, because it's a real auxiliary. Plus, I have everything, yes. With F tilde, the usual, and I close my parenthesis. Is it totally nice and easy? Yes, ask. So here is the Hermitian conjugate. So the imaginary part of a complex number, yes. It's a sneaky thing, but it's what it is. For at least a few years, 3 or 4 years, when I learned this, I didn't like it, so I was always writing with the imaginary plus, but then the factors, they come out a little bit wrong or different, so then I quit that I will write factors differently in the books, so now I write this. Okay, so we are completely amazing today. There is one last thing that I need to still do, that I will definitely start it now, and maybe I will do a little bit in the Q&A. And then we can write the most general n equal to 1 Lagrangian you ever wanted in your life. And what is the thing that we are missing? We know how to do scalars by themselves, chiral superfields, and we know how to do vectors by themselves. How do we put them together? Yes? So now we need to understand the supersymmetric version of what is called minimal coupling in quantum field theory. Or gauge matter interactions, however you want to call it. Okay, so let's do this. Let's assume we have a phi that transforms under gauge transformations. like this. It has to be like this because phi is chiral, so whatever transformation I do has to be chiral. The only thing I need to be careful here is when I write lambda, I need to remember to expand it in the generators in the appropriate representation, whatever is the representation that I want to study. Yes? That's all. So just choose your generators and you are done. Okay, this is amazing. But now, when we were writing before Lagrangians, we were writing like this, right? Full superspace integral, phi bar. Yes? Is this gauge invariant? No. Why? Because phi bar transforms with a bar. This doesn't cancel. We cannot mix oranges with apples, yes? Chiral with antichiral. So this is very bad. But it's not very, very, very bad because we know how to fix it. We will fix it precisely with minimal coupling, precisely the same way we did when we learned quantum field theory the first time. And okay, I have deleted it, but you have in your notes how e to the v transforms. E to the v transforms precisely in this way so that it cancels this, precisely. So phi bar e to the v, phi, so this, I'm writing the transformation of this. It was made to do that. Yes? So now you know what is the most general n equal to 1 Lagrangian. You write this as the matter part for the Lagrangian. You write this as the gauge part of the Lagrangian. The superpotential that we were writing before that leads to the scalar potential and everything, depending on precisely this choice. I mean, you have to really say, is this allowed, yes or no? But then that's it. That's the most general n equal to 1 Lagrangian that you can write down. Okay, I will not write it now, but I will write it in the Q&A session. And maybe also tomorrow I will start with that. But tomorrow I mean, we will also calculate, but I also want to do some very, very beautiful physics. So it's important that we have this now.